Our task is to use the Lagrange Remainder Theorem, namely that f at evaluated at a point x plus h is f of x plus h f dashed of x plus a half h squared f double dashed of x plus what's usually called a remainder term, which is a sixth h cubed f triple dashed evaluated at a point psi for some psi between x and x plus h. And the virtue of this is it's an exact equality, and so this remainder term provides an estimate of an error. Alright, so we've used this result to work out an approximation for the second derivative, that f double dash of x is approximately 1 over h squared f of x minus h minus 2 f of x plus f of x plus h. And this will be incredibly useful in computationally approximating differential equations. Okay, to establish this, let's start with the right-hand side. Okay, so 1 over h squared, and let's write f of x plus h first, minus 2 f of x plus f of x minus h. And this is 1 over h squared. Now, f of x plus h, we can replace that by precisely this. F of x plus h f dashed of x plus a half h squared f double dashed of x plus a sixth h cubed f triple dashed of psi. The minus 2f of x we leave the same. The f of x minus h, we apply Lagrange's remainder theorem, but with h replaced by minus h. So the first term is f of x as before. Place h by minus h, and we get minus h f dashed of x. Replace the h by minus h here, and minus h squared is just plus h squared, so this is a half h squared f double dash of x. Replace the h by minus h here, and minus h cubed is the same thing as minus h cubed f triple dashed of psi. Right, but there's a catch, an important catch. Right, these two xi's are different. Right, this xi has to be between x and x plus h, whereas this xi has to be between x and x minus h. So they're different things. So let's use slightly different symbols. Put a plus there to show it's bigger than x, and we'll put a minus there to show it's a bit less than x. Okay, now let's just simplify this, and a few things cancel straight away. We've got an f of x minus 2 and a plus 1. F of x, they cancel. Plus h f dashed minus h f dashed, they cancel. And let's see what we've got left. So there's the 1 over h squared at the front. We've got 2 half h squared f double dashed, so they add to h squared f double dashed of x. And then there's these two differences of the third derivatives, and that's plus 1/6 h cubed f triple dashed psi plus minus f triple dashed psi minus. Okay, so now this division by h squared can be done, and it cancels in front of the f double dashed, and then there's an h left here. 1/6 h f triple dashed psi plus minus f triple dash psi minus. It's an exact expression. So what we've shown is that the second derivative at x is equal to that difference expression with that as an error. And the key thing about this term here is it's multiplied by h. So if the step h in this expression is small, then this term here, the difference between these two things is small, and hence saying that f double dash is approximately this is a reasonable approximation. Now, many of you will know that f double dashed is approximately equal to that, to a better approximation than what I've got written here. And the reason is that these triple derivatives nearly cancel, this one minus that one. So when these nearly cancel, that means that there's really an extra power of h here. And with some more work, you can show that a better expression for the error is actually some coefficient h squared times something in the fourth derivative. So some coefficient h squared, fourth derivative at some point xi. But we won't do that here.